Okay, welcome back. So in this video, we are going to finish up our unit on waves and sound with a few applications of sound that we haven't all talked about already. We are not covering everything on sound, so there's a lot of cool things that we're going to leave out, but we're going to hit some of the more interesting things as far as I'm concerned before we move on to the next chapter. So talk about sources of sound and basically how musical instruments work for most of this video today. Okay, so the way that almost all musical instruments work that we use is by either vibrating a string. So I have a violin here that I brought in for today. Right when you pluck a string, it makes a noise. So we're going to talk about why you hear that noise. Or by having a column of air, such as this. Right, a recorder. Right, you blow into it, and there's a wave, a standing wave that's set up on the inside of this instrument that excites a sound wave that we can hear. So one thing to bring up about this is I have a tuning fork here. So this is something that we used to use back in the day before we had all of the stuff that we have now to try to figure out how to get something in tune. So right on here, I don't even know if you can see it, it says that this is a single note, and that number there, which I forgot to look at before I put it up here, tells you the number of hertz that is played when you do this tuning fork. So it's a 480 hertz B. So when I bang it on something, it starts to vibrate, and you might be able to hear it. So this is pretty quiet, okay? So we didn't really hear it. The way that we're going to end up being able to hear this better is right now, all it's doing is vibrating in of itself. So it's exciting a sound wave because it's moving in and out really quickly, but it's not exciting much of a sound wave because this in and out motion is really pretty subtle, pretty small. So we need something that will also vibrate next to this. And I'm going to use the table. And what I mean to show you this is that I'm going to hit it. I'm going to put it on the table. Did you hear that it just got louder? Move this closer to the computer. So there's this, and I put it on the table. Softer, louder, softer, louder. You might also hear when I first give it a bang, there's this really sharp noise, and then it kind of settles into a softer version of the noise. That's because some frequencies are resonant with this tuning fork, but when we hit it, all of the frequencies are excited. So it kind of sounds different in the beginning than it does after a little bit. Let me try that one more time. Sharpness in the beginning. Now. Okay, so instruments need not just to have a resonant frequency, but they also need some sort of sound box, like a resonance cavity, where we can get, remember resonance is this large amplitude response to a small amplitude forcing. So we need some sort of cavity where we can have our small amplitude forcing resonate. And in a musical instrument like this, right, the resonant cavity is the tube. In a musical instrument like this, the resonant cavity is actually this thing right here. And there's a lot of artistry that goes into designing a violin. This isn't a particularly nice violin, but it got me through high school. Right, and so the design of the interior of this cavity influences the quality of the sound, which is why a cheap violin like this you can buy for a few $100s. But if you want a gorgeous violin that is handmade and it has a beautiful sound quality, you'll pay $10,000 or more for that violin, because the shape of this resonant cavity in here really influences whether your string makes a normal sound that sounds maybe a little bit like something that hurts your ears, a middle school orchestra. I don't know if you've ever had the privilege of listening to an elementary or middle school orchestra, but it's not a privilege. It's a punishment, or something really gorgeous. And actually, one time when I was in high school, my instructor noticed that my sound wasn't sounding very good, and she checked, and actually there's a post on the inside of this, and I would try to show you it, but I'm sure we can't see it. That goes from here to here. It's called a sound post, and it had fallen down. Which is why it's always important when you have a violin or a stringed instrument like this that you actually keep some tension in the strings, because if there's no tension in the strings, your sound post might fall down, and that'll overall influence your sound quality in a pretty negative way. Okay, so we have already talked about this, but I'm going to throw it up here again, right? So for a stringed instrument, the strings, the ends of the strings are forced to be a node. So they look like this. So we have nodes and antinodes like that, and that's a review. But what about a wind instrument, right? On the end of a wind instrument, I have a hole. So what is forced to be true about the end of my wind instrument is that the pressure here has to be the pressure of the air. Okay, so on either end of my wind instrument, and also at the location of all of these holes that are exposed to open air, the pressure of the atmosphere around has to match the pressure at that hole. So we can force ourselves to have sort of locations where there is pressure that is the same on all of these dots. So we can set up a standing wave pattern that has this sort of spacing, okay? And so, right, and that is why, right, when I play a single note, if I put a finger right here, now this finger is no longer required to be atmospheric pressure, so it can be something else. And see, it didn't matter. It mattered a tiny little bit, but it really didn't matter much. So doing this hasn't really affected the standing wave pattern, but doing this has. So the various different combinations of fingers that you have here are going to make different standing wave patterns set up in here and make the sound that is produced to be pretty different. Okay, so for a wind instrument, they look like this. So wind instruments create sound through standing waves in a column of air. And this is what they look like on a microscopic level. So a tube that is open on both ends, that's what my recorder is for the most part, has pressure nodes. So the pressure is equal to atmospheric pressure right here, okay? And right, there will be these locations where there's compression, and then there's these locations where the air is expanded or there's a rarefaction. But everywhere that there is a hole, so on the ends or wherever there's a hole, that's where we have a pressure node. Pressure is equal to atmospheric pressure. So what's going on is that these air molecules are sloshing back and forth, pushing together and pulling apart, creating a standing wave pattern on the inside of this tube. So if you want to draw what pressure looks like, your book talks both about a couple of different things. I want to just focus in on pressure. And the reason that I want to focus in just on pressure and not everything is because if we're just thinking about pressure, then a vibrating column of air looks just like a vibrating string, okay? So the pressure nodes and antinodes for a column of air match the pressure nodes and antinodes for the displacement of a string as it's playing. Okay, so just like we had as the fundamental harmonic for a stringed instrument, the first harmonic and now the second harmonic has two nodes. The third harmonic has 3, and so forth. A tube that's closed at one end is a little bit different. So if it's closed at one end, then you end up with a situation where, well, we have atmospheric pressure over here on the open end, but on the closed end, we don't have to have atmospheric pressure. So we actually end up with a little bit of a different situation, okay? So for our open tube, right? That's the one that looks like this. I don't want to flip it over, so I'm going to kind of keep it. This is the string, but it's the same for the pressure, right? The fundamental frequency, F1, is, where is my equation sheet? Not here. Oh well. The fundamental frequency has a wavelength of twice the length of the string. Okay, so the wavelength is, this is half of a wavelength, so the whole wavelength takes twice the length of the string. Actually, it's a little bit different formula here. So open and closed, the fundamental wavelength, the lowest wavelength that can be resident in this cavity. Well, this right here is only a quarter of a wavelength. To get to half of a wavelength, we have to extend this out like that. So half of a wavelength takes 2 lengths of the column of air, which means that actually the fundamental wavelength is all the way up to 4 times the length of the string, which is pretty cool. I have a quick demo that hopefully will be something you can hear. So I have this pipe, and it's a pipe that is open on both ends. And if I hit the end of the pipe, it makes a sound. That sound is actually a note that we hear. But if I close one end of the tube, oh, I don't know, I should have tried this better. Let me get my cork. Normally this demo is done in a class with a helper to help me cork the end, but I don't have a cork this time, so I'm going to just have to do this myself. So when I play my note with it corked, and now uncorked, you hear it makes a different note? So the fundamental frequency has changed as I changed, as I corked the end of the tube. Oh, and we should just get this out of the way now. For those of you who don't have musical backgrounds, frequency is something that we perceive. So a high note, la, that is a high frequency, okay? A low note, la, that's a low frequency, okay? So we have the ability to perceive frequency. We can hear it, okay? All right, so I think we've already talked through this with the recorder, but I'll just show it here, right? So the first open hole becomes a pressure node, right, because it's open to the atmospheric pressure. And so depending on the pattern of which of these holes are open and closed, and this is a photograph of some very, very ancient musical instruments from a long time ago. So you can see we figured this out a very long time ago. And if you play a brass instrument, the way that you play is by like spitting into the instrument. So like a trumpet, a trombone, a tuba, a sousaphone, any number of those instruments. So those instruments will have a resonant in their cavity. And actually with your lips, as your lips vibrate, they are exciting all possible frequencies, but actually only a few of the frequencies are resonant. And so those frequencies that are resonant will be the ones that end up making the note. And the other frequencies that your lips are making will just die out. And it becomes very important when you play a brass instrument to have, I think it's called your aperture, a really good kind of set of lips that can carefully excite the right frequencies so that you make sure that you're playing all the right frequencies to get good sound quality. Okay, so let's add in quality of sound, and I want to do, it's going to take me just a second to get it working. There we go. Okay, so I have here move this Okay. So I have here plotted what's called an FFT graph. It's a fast Fourier transform. So what a fast Fourier transform is something that is going to tell us the frequencies that are being excited as we play a note. Okay. Let me make this even bigger. Just want to be able to make sure that we can see it well. Should have gotten this set up beforehand, but you know, you do what you got to do. Okay, so we can see the frequencies that are set up. So as I talk into this microphone here, let me get it running. Of course, it has stopped working. As you know from days long past, when you actually had to come into lab. All right, well, this isn't working, so I'm going to have to stop this video and I will start up with the next one.